Okay, AP Statistics, we are still in Unit 6, yay for us, and we are looking at example 12. I don't know if you remember this, but in the last unit when we talked about discrete distributions, this was one of the examples that I gave you to find your expected value and your standard deviation. So we have a large quantity of ostrich eggs that are placed in incubators at different temperatures. The probabilities of the eggs hatching are given by the following distribution. So, of course, I give you the distribution here, and I give you various temperatures at which the eggs would hatch. And then in the other row here, I have the probabilities of eggs hatching at those particular temperatures. Now, I know that we're not dealing with discrete distributions in this particular unit, but it is going to serve to further establish how we transform values from one unit of measure to the other. So that is why I'm using it. The first thing I want to do is to remind you that when I'm asking for the expected value, I do want the mean. And of course, this is given to you in degrees Fahrenheit. So the mean in Fahrenheit, we're going to find in Staplett here in just a moment. And then for part B, we're finding the variance and standard deviation of the temperature in degrees Fahrenheit. So degrees Fahrenheit is where we're working. We're not going to worry about the variance for now because we don't really need it for this particular problem. So I want to find the mean and standard deviation for Fahrenheit. So I'm going to take my table, and if you'll remember how we do this in Staplett, I am just going to visit Staplett, and I'm going to choose under normal distributions, discrete random variables. And we're not going to name this because we don't really need to. So I've got 5 temperatures here. So I'm going to add a few more of these here. So I am going to now put in my value. I've got 99 degrees Fahrenheit, and the probability is 0.2. And then I've got 100 with its probability of 0.15, 101, the probability of 0.3, 102, probability of 0.3 as well, and then of course 103, and we've got a probability of 0.05. Okay, so I'm going to begin the analysis here, and I'm just doing this to get my mean and standard deviation. And down here at the bottom, as you can see in the little table under summary statistics, my mean is 100.85, my standard deviation 1.195. Okay, so now I am going to go back to my problem here. So I've got 100.85 degrees Fahrenheit for my mean, and for my standard deviation, 1.195 degrees Fahrenheit. Okay, so C and D, now we're really going to explore what this transformation would look like. So the only thing that would be different from how I'm doing this problem for a discrete distribution versus if I had given you a normal distribution is that I probably just would have given you this information and told you it was normally distributed. So working from here now, I am going to transform my Fahrenheit temperature into terms of Celsius. And I don't expect you to remember that formula, but I have given it to you right here. This is how we transform from Celsius to Fahrenheit and vice versa. Since I want it in Celsius and this equation is set up for Fahrenheit, I am going to solve this equation for Celsius so that we know how to do this. So I'm just going to explain that to you. I'm subtracting 32 from both sides. So I end up with 9/5 Celsius equals Fahrenheit minus 32. And then I'm just going to multiply both sides by the reciprocal of 5/9, or the reciprocal of 9/5, which is 5/9, to get Celsius isolated. So I've got 5/9 times Fahrenheit minus 32. So this is the transformation equation I'm going to use. So when I want my expected value of the temperature in Celsius, I want my mean in terms of Celsius. Transforming means super easy. I'm going to take this equation, substitute in my mean or expected value in Fahrenheit. Bam, I'm going to get my answer in, Celsius. Okay, so I've got 5/9 times the Fahrenheit expected average, the expected value, and then subtracting 32. Okay, I know that for all of you math scholars out there, I don't need to remind you of this, but please follow PEMDAS. You must subtract these two values before you multiply by 5/9. I'm just throwing that out there. Anyway, so the answer you get here is 38.25 degrees Celsius. So that's going to be our average temperature in Celsius. Okay, for part D, I don't need my variance here. I'm just finding standard deviation in Celsius. So I'm going to use my same formula, but I want you to notice, okay, I want you to remember that one of the rules for transforming for our standard deviation, we don't care about the constant being added or subtracted. So I don't care about the -32. I don't need it. All I'm going to do is take the 5/9, substitute in my standard deviation in Fahrenheit that I got up here, and then I am going to simply multiply those together, and I get 0.6639 degrees Celsius. Easy peasy, lemon squeezy.